Sashimi, you can see my slides, right? Okay, so good morning, everyone. So we will continue what we were discussing, and I'll start with a maybe 5-minute recap. So we are, formally discussing a historical overview of OS, but actually it's not completely history. We are actually seeing how, computer systems have evolved over time. So at the very beginning, we had batch processing systems, where at any one point of time, only one job used to be in the system. So the simple organization, the memory consists of a part of the OS, a part of the memory has the OS loaded, and the other part has just one program. And as long as this program runs, all other programs have to wait. So so that is the name, that is what is implied by the name batch processing, right? So, but clearly the CPU is underutilized because, let's say, a program spends lots of time in I/O, and I/O is usually slow. Still, all the other programs have to wait, and the CPU remains idle as long as the program is doing I/O. So clearly, people were not happy, so they went for multi-programming. So what is multiple programming? So first important deviation is that multiple jobs are loaded into the memory at the same time. And the OS, a particular part of the OS, decides which job will be allocated the CPU. That part is called the scheduler, the job scheduler. So people understood that when one program is doing I/O, the CPU can be allocated to another program. So that will interleave the I/O and CPU usage, and hopefully things will get more efficient. Right? So, of course, this comes at some added complexities. For example, suppose program A is running, or job A is running. Now it asks for I/O. So the OS will now allocate the CPU to some other job B. But for that, it needs to be ensured that we remember the A's context. That means at what stage was A interrupted? Because we will have to resume A from that place only. Okay. So those additional complexities are there, but overall systems became more efficient. That when A is doing I/O, maybe another job B is being able to use the CPU. Once A's I/O is finished, then the scheduler can choose to restore A. So therefore, the added complexities are that there needs to be some mechanism to store the context of a program which has been interrupted, let's say, because it asked for I/O. Also, because we are now allowing multiple jobs to be on the computer's memory at the same point of time, we need memory protection. We cannot allow one program to disturb the memory of another program. Also, we need a privileged mode because clearly, let's say these decisions, which program will run when, etc., these cannot be left to user programs. So these has to be special powers which are taken only by the OS. So we need a privileged mode of execution. Basically, we understand that there should be some instructions which are only allowed to be given by the OS, not by user programs. So this is multiprogramming, what we discussed. Now, inherently, if you understand that multiprogramming has a assumption that we will have a good mix of CPU-bound jobs and I/O-bound jobs. CPU-bound jobs are those which will spend most time in their lifetime doing CPU operations. And I/O-bound jobs are those which spend a lot of time doing I/O. I'm sure you have written both types of programs. Like you have written programs which take a lot of I/O and do a lot of printing and so on. And also you have written programs which maybe just take one small input and give one small output at the end. I mean, take one small input in the beginning, give one small output at the end. but does a lot of computations in between, right? So multiprogramming essentially assumes inherently that we will have a good mix of some CPU bound jobs and some IO bound jobs. However, what if that is not the case? It often is not, right? When we write programs, we usually don't care about CPU bound, IO bound, and so on. We just write what we are required to do. So often it is the case that we may not have a good CPU bound and IO bound jobs. Let's say in a particular situation, all the programs that are currently in the computer's memory are CPU bound. Okay, so none of them are doing IO. None of them is doing IO. All require lots of operations on the CPU. So one simple solution would be fine. Let the first program finish. Allocate the CPU to the first program. Let it go on as long as it takes. Then once it finishes, allocate the second program. Again, wait until the second program finishes, then allocate the third program, and so on. Sure, this could be one solution. Any other solution coming to your mind? Anyone? So let's say we cannot interleave CPU and IO because all our programs currently in the computer's memory, they are CPU bound programs. But still, we would not like, let's say, all other programs to wait until only one program completes. So can we do something else? What do you think?
Run concurrently.
Okay. So Nisarg says time sharing, and okay, the answer given was run concurrently, but again, yeah, would be fine. It would be better if you just write in the chat, but fine. So yeah, so time sharing. What do you mean, Nisarg? Can you unmute and say?
Sir, run each process or program for a small period of time, shift to something else, and keep doing this.
Right. Good. Exactly. So that is what we are going to discuss now, which is called technically multitasking. So previous one was multi-programming, now it's multitasking. So multitasking or time sharing, which Nisarg used the term. That's a logical extension of multi-programming. And here we again have lots of jobs or programs in the memory. And the CPU goes on switching the operating system goes on switching the CPU among all these jobs so fast that users can interact with each job while it's running. Okay, so let's say just as an example, don't take these numbers which I'm going to say very sacrosanctly. Let's say there are 100 jobs, so each second is divided into 100 time periods, and the OS allocates the CPU to every job for 1/100th of a second. Again, do not take these numbers too sacrosanctly, but that is the idea. So you will divide the, say, 1 second as if the 1 second is divided into 100 parts, and one part is allocated to every program. So every program gets the CPU for 1/100th of a second. Well, you might think, isn't that too slow? Isn't that too small? The answer is no, because the CPU can actually do lots of operations even in 1/100th of a second. The advantage is that we human beings, we won't even understand that our program was not running always. So let's say, even if, say, we are seeing a GUI kind of thing, even if that GUI is refreshed once in every, even if the GUI is refreshed once every second, let's say, or twice every second, to our human brain, it will seem as if we are always seeing the GUI. Okay. So So that is the idea of modern computer systems, that the CPU switches jobs so fast that users don't even understand that their job is not always running, and they feel that they can interact with each job while it's running. So this is how we now have interactive computing. Okay. So even in multiprogramming and batch processing, of course, there was no concept of interaction. But now, as if we are dealing with programs in real time, or we are doing interactive computing. So nowadays, with the processors getting so fast, and of course, a lot of other mechanisms are involved, which we will discuss throughout the semester. But basically, now the CPU is switching jobs very fast. Right. So now even we can do real-time scheduling, as in maybe there are some, we are not going into details, but there are systems called real-time systems where it has to be guaranteed that every job will meet a particular deadline. Right. So those kind of things are possible now, because let's say it is guaranteed, if you can guarantee that this job will be given the CPU once every at least say k time units, then you can guarantee that the job will be completed within this time. So now the concept of like meeting deadlines for jobs, etc. is possible. And of course, understand that we are doing all these because we want to get better sharing of resources. The CPU itself is possibly the most important resource. So we are sharing it among many programs. Plus memory, etc. Everything is being shared among different processes. Okay, Yashika has a question. How does the OS determine the deadline for a job? No. The OS does not determine the deadline for a job. The deadline for a job is decided by an application or by a user. Okay. So, I mean, in these kind of systems, the deadlines are assigned by the application or the user. The OS has to, in a real-time operating system, those are special types of operating systems, which we are not discussing in this course. But in those real-time operating systems, the OS guarantees that if a deadline is given, then that job will be done by its deadline. So the OS is not determining the deadline. Is that fine, Yashika? Okay. Okay. So now we are talking about the concept of CPU scheduling in this time sharing mode. So basically we understand that we need to we need to switch the CPU from one job to another after every certain time interval. So naturally we need some mechanism to keep track of time. Specifically, we need hardware timers. Okay. Yeah, okay. Moinak has given a pointer. So if anyone is interested in real-time operating systems, then you might look up the web for Litmus RT. So Litmus RT is like a real-time operating system. Again, this being the introductory course on operating systems, we are not going to discuss specialized operating systems like real-time operating systems. If anyone is interested, please look up Litmus RT.
And just if I may,
Sure.
just one thing about the deadline, Trishika and to others, when deadline is needed, you're running a car, say a little bit higher end, because that will have a full-fledged operating system, say a BMW S-Class or something. And when you actually click, press the brake, there has to be a deadline before it stops. And that's a hard deadline.
Right. So actually, thanks, Mainak. So real-time operating systems are used for like very time-critical jobs, as Mainak said that. I mean, if a brake has been pressed in a car, then if the operating system says, oh, there were too many processes running, that's why the effect of the brake got delayed, then there will be a catastrophe. So those kind of things to be taken. I mean, those kind of applications need such deadlines. or aviation like traffic, train or flight traffic and so on. So if a control has been, if some administrator has issued a control signal or a making a traffic light red or something, then it has to be done within a certain amount of time. Otherwise, it cannot get delayed. Okay, so okay, so you see, so to implement these multitasking systems, we need hardware timers because someone has to keep track of time. Because maybe after every interval, some action needs to be taken, like the CPU needs to be switched from one job to another. Also, for the same purpose, we need a scheduling algorithm. So there are lots of tasks in the computer's memory. Maybe there are 10 tasks which are ready to run. So next, the CPU should be scheduled to which task, right? That is the job of the scheduling algorithm. So we will spend quite some time on the scheduling algorithm in the course. Also, this is an important concept, the context switch overhead. See, we are telling that we want to have multiple processors in the computer's memory, and we want to switch the CPU from one process to another. We are doing this so that we can better utilize the resources like the CPU. But understand that the ultimate goal of the CPU is to execute the user programs. So the amount of time we are taking to switch the CPU from one program to another, that is actually an overhead. Okay. So again, we need to minimize that overhead. So let's say a particular second, if you think, maybe there are 10 programs running and we want to give some amount of processor. We want to allocate the CPU to each of those 10 programs. So 1 second, if we divided it into 10 parts, so every part 0.1 second. Now, if we say that, okay, every program will get 0.1 second, that is ideal, but that is not practical. Because you see that between two programs, like one program A was running, then the CPU should be scheduled to program B. Between these two, the operating system should run for some time. Otherwise, who will allocate the CPU? Okay, so nothing happens unless a program runs. So suppose program A is running. After that, we want the CPU to be scheduled to process B, or program B. Between A and B, the OS must run for some time, and that part the OS will actually schedule the CPU to B. So that small time for which the OS ran, that is actually, you might think, overhead. Because ideally, the CPU should only be used to run user programs. But we need to give some time, we need to allocate the CPU to the OS also. So that part is called the context switch overhead. And we have to worry about keeping this small. And that is why we do not want too many context switches. And that is why the concept of CPU bursts and IO bursts. Like lots of CPU operations collected together, or lots of IO operations collected together. That is how we want to run programs, so that context switches are minimized. This is what we were discussing slightly yesterday. Like let's say your C program prints out one character in every iteration of a loop. Do not think that every character, when you put out a printf statement, so printf, every iteration of the loop prints out one character. Do not think that every time there will be a context, your program will actually go for IO. That would become, then your program will suffer. There will be lots of context switches because every time your program asks for IO, the OS needs to run. But better collect outputs together in some buffer And maybe when you have already output a certain number of characters, then you go for an IO operation and output all those characters to the monitor. Okay, so that is like we are collecting IO operations in some buffer so that later on we can do an IO burst. That means lots of IO operations in one go. Okay, so that was our discussion on multitasking. Any questions at this point? Okay, if not, let me proceed. So now we will discuss about today's operating systems, which are actually multitasking operating systems like Unix. So let us get some more insights into them. So for multitasking, as we discussed, that someone needs to schedule the tasks as time goes. So scheduling the task means allocating the CPU to a particular task or a particular program. Okay, one small point here. I'm using several terms interchangeably, like task, program, right? So for the first few classes, we will just go on uh, using these terms interchangeably. But say in a few classes, we will actually converge to one term, which is called process. So that is the technical term. So then after, subsequently, we will mainly talking about processes. Okay. But for now, I'm using these terms like task, program. Maybe sometimes I'm also using the term process. Just think that all these are interchangeable for now. Basically, so any job or any task that you give, like your C program running or a word processor running, that is a task or a job. So someone needs to schedule these tasks or programs. So, and clearly kernel does it, and it uses the timer. Now there has to be some dual mode of operation. What is that? Let's see. So a process or a task can execute in two modes, the user mode and the kernel mode. Kernel mode is also called privileged mode. So in the user mode, you run normal tasks. And in the kernel mode, you directly talk to the CPU or peripherals to schedule tasks. And there is a mode bit provided in the hardware, which tells the CPU whether it is running in the user mode or kernel mode. So clearly say your programs, like your C programs are running, or you are running some standard program, then the CPU will be in user mode. But at some point when the kernel is running, the CPU will switch to kernel mode. Okay. What is the specialty in the kernel mode? That there are some instructions which are special, which are called privileged instructions. Those instructions can only be run in kernel mode. If you try to run these instructions in user mode, there will be an exception, or you will not be allowed to do that. Examples of such privileged instructions are like low-level IO operations, setting protection registers, or running EI or DI instructions, etc. EI is enable interrupt, or DI is disable interrupt. So, quick question. Why do you think EI and DI are privileged instructions? Why not make them normal instructions? Okay, any answers? Okay, Nisarg is saying a process can illegally access memory without any interrupt. Okay, Nisarg, I mean, see, maybe the instruction to access memory, I mean, if we are worried about, if what you said, that is the only thing we are worried about, then we could make the instruction to access memory a privileged instruction. So then a normal user would not, I mean, a normal user program would not be able to do that. So the idea here is if you make the EI and DI instructions, I mean, user level, I mean, not privileged, then say a malicious program will simply itself call disable interrupt. And then no one will be able to switch this program out of the CPU. So it will hog the CPU. Okay, so I mean, let's say a malicious program simply at the very beginning, it disables interrupt and then it goes on running. So because it is not, because it has itself disabled interrupts, I mean, if it is allowed to, then even the OS might not be able to run anymore. Because that program, let's say, is written in such a way that it does not raise any interrupt. It does not make any system call, etc. It just goes on doing some CPU operations. So, and it has disabled interrupt. So then there is no way even the OS can get back the CPU. So that cannot be allowed, and therefore this enable instruction, enable interrupt, disable interrupt instructions are privileged. Okay, so you see that I mean some instructions need to be privileged so that any program cannot run it. So now we are talking about two modes, right? The user mode and the privileged mode. The question is, when will the switch occur between, say, from user mode to kernel mode and vice versa? So the answer is given in this slide. When there is a system call or an interrupt, that changes the mode from user to kernel. And there is a special return instruction which changes the mode back from kernel to user. So when does this changes occur? Let's see. Suppose a user process is running, like your C program. So clearly the CPU is in user mode. Now your program makes a system call. How? Let's say a simple scanf or printf. Even that will do a system call, right? When your program does a system call, then the mode changes. So maybe you are doing just a library call, but then inside that library call, printf scanf, the system call is made. So when the system call is made, that means you are asking the kernel to run. You are asking for some kernel code to run. Then the mode changes to kernel mode. And the syscall handler, that means the function of the kernel that you asked to be run, that runs. After that is completed, then there is a return, right? So let's say the control is again coming back to your program. At that point, the mode changes back to user mode. And then your program again resumes operation. Okay. So this is how mode changes occur. I mean, when your program is usually running in user mode, when it does a system call or it asks the kernel for some service, then there is a mode change to kernel mode. The kernel code runs for some time. And when control comes back to your code, then again the mode changes back to user mode. So that was our discussion on the dual mode of operation. The final thing, I mean, in this deck of slide is the use of the timer. So recall that the operating system divides the tasks into micro tasks and then schedules them in the CPU. See, understand this. When the program that you have written, the whole of it is not being executed at one go. Maybe your program was allocated the CPU for some time. Maybe 100 instructions could run. After that, your program was the CPU was allocated to some other program. So the state of your program will be saved. Later, at some later point of time, when the CPU will again be allocated to your program, then that saved state will be used to resume your program. Okay, so we all feel that our programs are running at one go. Our programs are always running, but actually that is not the case. So basically, the operating system uses a timer to prevent resource hogging. That means, let's say that your program is not making any system call. See, let me go back to the previous slide, this one. So you see your program. So one way of the mode changing from user mode to kernel mode is that your program itself makes a system call. Then as if you hand over control to the kernel by making the system call. But suppose you have written a program which does not make any system call. It does not do any printf, scanf. It just, goes on doing computations. Right. So let's say I can always think of a program which, let's say, does not take any input output, only it has a large array which it kind of fills up with numbers and then goes on doing matrix multiplication and so on. So your program is not making any system call. So does that mean that your program will be allowed to run throughout? Like if it takes 2 hours, no other program will run in these 2 hours? The answer is no. So that is why the timer is used to prevent such resource hogging. So now this part is important. When the operating system schedules the CPU to your program, before that, it also sets the timer such that the timer will interrupt the processor after a pre-specified time. Okay, so the operating system initializes the count value of the timer. I think you kind of have read about timers and all in some earlier courses like digital logic or something like that, right? So that kind of a timer you're talking about, you set a count value. That count value in the timer is decremented by the physical clock. And when the count value reaches 0, then the timer will generate an interrupt. Okay. So let me repeat. Before handing over the CPU to your program, the operating system set a timer. That means initialize the count value. Of course, this is done in privileged mode. Now the count, then the CPU is scheduled to your program. So your program starts running on the CPU. However, in parallel, the timer is also getting decremented by the physical clock. And when the timer reaches 0, the timer generates an interrupt. Because an interrupt has occurred, now the kernel wakes up. So now your program will not run anymore on the CPU, rather the kernel will run. And possibly the kernel will schedule some other program. That means we'll allocate the CPU to some other program. First, it will save the state of your program, and then it will allocate the CPU to some other program. Okay, so understand this part very carefully. Like we often hear, when we ask people later in the Viva and all, that's how is the CPU switched from one program to another? We often hear the answer as, a program A is running, then the scheduler comes and schedules, and allocates the CPU to another program. But if your program is running, suddenly the scheduler cannot start running, right? At one point of time, only one program runs. So this is the underlying mechanism that before allocating the CPU to your program, the OS has set the timer, and the timer will interrupt, and then the kernel will start running. It will save the state of your program, and then it will schedule the CPU to some other program. Okay. Any questions here? This is an important part, so if you have any doubts, please feel free to ask. Okay, Vijay is asking, how will the timer decrease time when a program is running? See, this is the answer. So this is a hardware, piece of hardware. So it is decremented by the physical clock. So every computer system has a physical clock, and that is what is used to decrease the timer. So it's not like a program running where, for the loop, value is reducing one by one. It's a hardware piece, a piece of hardware, which is decremented by the physical clock. Okay, so this for decrementing the timer, it does not mean that the CPU needs to be involved. The CPU at that point is running your code, let's say, your instructions. The timer is decremented by the physical clock. Okay. Yashika is asking, is the timer value set the same for all processors? If not, then how do they differ for different processors? Okay, that's a good question. I would imagine that the timer value is set more or less the same for all processors, but there can be some exceptions. Maybe if there are some priorities associated with processors. We'll discuss these later, but I mean, if it is somehow no, so one simple idea is that all processors are treated equally. Then I would imagine the timer value is set to the same value for all processors. But if all processors are not to be treated equally, if there is, let's say, some priority among the processors, then I can imagine that the timer value being set a bit differently. For high priority processors, maybe they are allowed a more amount of time in the CPU. But I think, for simply speaking, you can think that for now the timer value is set the same for all processors.
So can I say something?
Yes.
So is it the same for the privileged and the non-privileged ones, like processes timer? For all the processes, can we consider the same logic? Like it will be almost the same.
No, wait. First of all, you use the term privileged and non-privileged. So
yeah,
understand this, that like we never spoke about privileged processes and non-privileged processes. What we said when we were discussing that privileged thing, we were saying that there are certain special instructions which can only be run in the privileged mode or kernel mode. And that is usually done by the operating system itself or the kernel. So we never talked about user processes, some being privileged, some being not privileged. Those privileged instructions were run by the kernel itself. So like you asked that is the timer value set the same for all processors? I said that in general, I would imagine that is the case. But in some special circumstances, maybe there are some exceptional operating systems which recognize that some processes, some user programs have higher priority than other user programs. And for them, it might think of giving more time to those high priority programs. But this has nothing to do with the privileged mode and non-privileged mode that we discussed.
Yes, got it. Thank you.
Okay, I see a question from Srijanak. Okay, Srijanak, can you unmute yourself and ask the question? Because I want to clarify some things about the question itself.
Yes, sir. So what do you want to clarify?
So tell me the question once more.
So like here you explained that let's say my program doesn't have any printf scanf, it just takes an arrow and goes on running. So if my program has printf scanf and it wants to invoke an interrupt at some point, does it still wait for the timer to reach 0 or something?
No, okay, see, your program does not have any knowledge about timer, right? Like, have you ever written a C program considering that a timer will be there, which will at some point reach 0, etc.?
No.
No, right? So your program does what it has to do. Like if at some point your program needs an input, then it calls scanf. At that point, control is handed over to the kernel because you have called scanf, which will in turn call a system call. Right? So as such, your program has nothing to do with the timer. But what I said is that suppose you write a program which does not do any system call. It does not take any input, output. It just goes on executing instructions on the CPU. Even then, this program will not be allowed to run forever. That is where the mechanism of the timer comes in, that before giving the CPU to your program, the kernel sets the timer so that after a certain amount of time, the timer runs and then control goes back to the kernel. That means when the timer will raise an interrupt, the kernel will start running. So this is as if that, let me take an example here. So suppose like see, let me assume that see Srijanak, we are using a shared medium, right? Where I am talking, you are talking. For some time I gave the medium to you. I told you to talk. But I need the guarantee that at some point I'll be again be given the medium. If that is not guaranteed, then then the whole system will fail. So similarly, the kernel is allocating the CPU to say your program. There needs to be some guarantee on the part of the kernel that at some point it will again run. Otherwise, it cannot give the CPU to some other program. So that mechanism uses the timer. So that kernel sets the timer before giving the CPU to you, with this intention that the timer will run, at some point the timer will interrupt, and then the kernel will again get control to the CPU. Okay, so control can go back from, so your program, let's say, is running. There are two ways in which control can go back to the kernel. One is that your program itself makes a system call. Then you ask the kernel to be run, therefore the kernel ran for some time. The other is that you did not ask the kernel to be run, but because the kernel had set the timer interrupted, and therefore the kernel again started running. Okay, Srijanok, if it is not clear, then ask again. This part is important, so it is important.
So, sir, like you said that the timer is set for every program, right? So how does it know when to use the timer, time scheduled, or when to use the syscall from my program?
When does who know?
Like when does it know when to interrupt based
What
on
is
my
it?
syscall?
Wait. You are asking how does it know? What is it?
OS.
Okay. Now again, that is why I said, I mean, sometimes if you ask the question correctly, half the answer is obtained. So now again, frame your question.
So how does the OS know when to interrupt?
How does the OS know when to interrupt? Whom will the OS interrupt? And how? Because see, when your program is running, the OS is not running.
Yes.
So there is no question of the OS interrupting your program. At this particular point of time, if your program is running, the OS is not running. So the OS has interrupted your program. That does not make sense.
Okay.
Tell me, so I think this discussion is helping others also. Even if anyone else has some question, then because this is important to understand. This is the crux of the course. So if you have any question, tell me.
Yes, sir, but like I still didn't understand.
What did you not understand?
Like how, like what, like if you ask me what is it, so what is that it?
No, what is the question? Tell me that. What do you want to know? What did you not understand?
So you said that if my program invokes the interrupt, then it will do that, and if it doesn't, if it wants to take all the time, then the timer invokes the interrupt after a fixed time. So
Yeah,
which one to choose?
No. Which one to choose? See, that completely depends upon the program that you have written. If you have written the program which makes a scanf or a printf call, then what is shown in this slide will happen. But if you have written a program which does not do any system call, which just goes on doing computations, even then, at some point the kernel will reclaim the CPU, and that is happens through the timer mechanism.
Okay.
If you need, see, I mean, you will do a system call if you need it. If you don't, you won't. So even if you don't do a system call, at some point, and that is the timer mechanism. Okay, now Animesh has a question. Okay, I'm confused with this question. So Animesh,
So
do
basically,
you mean piped input?
so when I run from the terminal, I can do /a out, and then I use the greater than or less than sign for redirection, right? So, or let's say I'm using bash and I'm using the piping operator to shift the input to my C program. So is there a difference between when I am typing from my keyboard, that like from what I think that should take longer as compared to when bash is piping the input from from the execution of one thing to another. So does the OS make a difference between the interrupts then?
You are mixing up too many things. Wait. First of all, let's say the examples which I was giving was that a C program is running. Now you are bringing in bash,
So my question is not like directly related
which
to
is
what you were
another.
saying.
Mhm.
So like given that I was working on the assignment, that is why I had this doubt. So uh, so let's say I'm running a dot out from my terminal. So many times I give the input via through a file, but I just redirect the input stream to a file. So I use the greater than or the less than operator for that. And bash does that. Bash reads from a file and puts it to the C program to scanf. So compared to that, compared to when I call scanf, but I do not do anything like that, I type it from my keyboard. So me typing from my keyboard will take orders of magnitude more time compared to bash reading from a file and putting it to scanf. So does the operating system have any way to know that what is the overarching context that one will take less time, so it should treat the pipe like the redirected C program differently from the one in which I'll be typing? Does it have any way of knowing that?
Okay, no. Again, I am still confused about. Uh, so Moinak, I mean, if you have an answer to this question, you say. But I mean, yeah, I'm seriously confused what to say here because this.
So I think I sort of understood what Animesh is saying. So let me actually try to understand what you are saying, Animesh. Okay, very quickly. And so you are basically saying that this input, taking the input, can happen in multiple ways. One of them is you are actually using scanf, where I need to, or you need to actually type in writing like yes, no, blah blah blah. That will take some time. Say take time X, and then you can also redirect or using pipe to give the input to a code which will take Y time. Definitely what you have seen, Y is much lesser than X when you are just writing the whole pipe and just press enter. So your question is that does Waze do any sort of optimization or knows that Y is less than X and then use it for scheduling or like setting the timers? Is
Yes,
that correct?
exactly. That is exactly my question. Like, why would be orders of magnitude smaller than X? Because when I'm typing, I take a lot of time to type compared to
Mhm.
bash read.
Yeah. So the answer is that no, the OS doesn't really know the context that you might have guessed, right? OS is not really that smart. It doesn't know the context what you are trying to do. So what OS does though, it basically, however, OS knows using, or basically the coders of OS actually told that using some signals. What do you mean by signals? So whether you are doing a scanf or you are doing a pipe, all of them will ultimately goes to OS. Why? Because scanf is taking input from the terminal and from the keyboard. So the OS needs to act as a mediator between the keyboard and your code. Similarly, when it is taking input from pipe, it needs to take input from terminal, which is another device. In Linux, like device means basically your computer screen. So it needs to be, everything will be bogged down to the component system calls. So whatever system calls are you asking for operating system to do, they would know that whether you have to take input from keyboard or whether you need to take input from display because you need to give the device ID. Then what operating system does, it will actually keep track of how much time is passed while taking the input. If it is taking too much time in taking the input, then it will again assign, like this is called IO intensive tasks like IO burst and CPU burst, which we'll talk later. But essentially, just by measuring how much time does it take to complete those system calls, OS try to reschedule and try to make sure the response time remains the same for all. So OS definitely does something smart, but not within knowing the context of whether we want to actually do it via the keyboard or via the terminal using pipe. All it knows is that something took a lot of time, so it is a good time to possibly stall it and give others a chance.
Thank you. clears it a lot.
Okay, thanks, Mainak. I see another question by Aryan. If every program themselves makes system calls at regular intervals, then can we say timer is not required? I would not say that. First of all, there is no way of guaranteeing that, first of all. Right? And because you cannot, I mean, the OS or anyone cannot guarantee that everyone who writes a program or different programs will write their program in such a way that they would make syscall at regular intervals. And second, there is also another reason. See, actually our next discussion, which we will start next day, is about syscalls. So the idea here is that not all syscalls will be handled equally. So see this program here, so in this big slide which is being shown, let's say that this user process called a printf. So this syscall handler is the one which will handle printf call or print something on screen, let's say. However, when the timer interrupts, that is a different system call, and a different part of the kernel will handle that timer interrupt. So I hope you understand that the kernel code which will run if you call printf would intuitively be different than the kernel part of the kernel which will run when the timer interrupts. So when the timer interrupts, the particular part of code kernel which runs, its function is to allocate the CPU to another job, which is different from what is happening in this slide, let's say. So don't think that the same part of the kernel runs always whenever there is a system call. It very much depends upon what type of system call has come. I mean, your program calling printf and so the timer interrupts is not the same. Let's say even for you, let's say, I hope you answer your program calling a printf versus your program trying to access a bad memory. Clearly, the two functionalities are different. Okay, so what part of the kernel will run will depend on what system call has come. We will discuss these details of system calls starting tomorrow. And I mean, the topic would be the system calls and interrupts. Fine. So any other question today? Otherwise, we can end today's class. Okay, then. Thanks, everyone. See you tomorrow again.